Hello guys, today I will talk to you about volatility forecasting. My agenda includes 4 topics. First, the introduction of Akirai's work, which I base my work on, then my data or the data I've used for my work, then the model estimation, and then the forecast of return variances and volatilities I've got from those models. First, Akirai's work. Vedat Akirai published a paper in 1989 called Conditional Heteroscedasticity in Time Series of Stock Returns, Evidence and Forecasts. He divided this up in basically 4 different parts. First, he investigated the statistical properties of return distributions. Then he identified return-generating stochastic processes which are consistent with the found statistical properties, statistical testing of the fit of arch and gauge models, and then he compared various forecasts of market variances with the actual variances. I will focus on that. The Akirai paper was based on CRSP data from 1963 to 1986. The main purpose of this study was to update his findings, see whether his results hold true for different time frame and a different market. I used the DAX index and got the price data from the API of Yahoo Finance with the library pandas of Python. We got the price data then and calculated the daily return series. We can use that to plot different things. We can use plot the return over time and the cumulative return of the DAX in the selected time frame. The data is divided now into 4 periods with each 6-year long time frames. The model estimation. Each period contains now 72 months for 6 years. 48 are used for model estimations, 24 for out-of-sample model testing. The actual variance needs to be calculated first in order to have a benchmark. This is done by summing up the last 20 squared returns to have a realized volatility or variance. 4 forecasting models are used and compared. The historical average, exponential moving average, arch and gauge model. The historical average is simply put just an average of the last 12 variances. The exponential moving average is calculated over the last 12 months using a moving constant W. This moving constant is calculated by minimizing the sum of squared errors of the EMA compared to the actual variances for different W. You can see this on the right hand side for each period. The arch model. The arch model is defined as follows. I will not explain the equations since we've learned about them in class. For the model estimations, the arch library of Python is used. The value for P is chosen with the use of the AIC criterion. The arch model is estimated for each trading phase of each period with different P's, and then the P with the lowest AIC is chosen. Here you can see that for period 1, period 9 yields the lowest AIC, thus we used an arch 9 model. To see whether the model is a good fit, the autocorrelations for different legs of the model's residuals are plotted on the left hand side. There's no real serial autocorrelation, so we assume a good fit. Additionally, Young box tests were done for different legs and their p-value plotted. You can see that the p-values are always very small or even 0, thus we have achieved a good fit. Now, what do we do to get a forecast? For both models, for both time series models, we use successive out-of-sample forecasts. First, the model is fitted for the training phase of each period, and the first 20 future data points are forecasted and the forecasted variance is calculated. After that, the first 20 days of the training phase are dropped and the 20 previously forecasted realizations are added to the training phase. And now we have a new training phase and estimate the model again and forecast the next 20 future data points and so on. So we have a successive out-of-sample forecast. The 4 forecasting models have yielded now 24 forecasted variances for each testing phase of each period. We can plot these results with the actual variance observed in the testing phase. The actual variance is the blue line, the purple line is the gauge, the red line is the arch model, the historical average is the orange one, and the green line represents the exponential moving average. We can also calculate error measures for statistical evaluation of the forecasting models. We have the mean error, mean average error, root mean squared errors, and a mean average percentage error. The table here shows those different results. You can basically see that the averages don't perform as well as our time series models and the gauge model the best. What are the results? The average forecasts do not perform well and are too smooth and does not reflect continuously changing nature of stock return variances. As you can see here, they are not able to capture those spikes. On the other hand, the time series models intuitively perform better and are even able to forecast sudden volatility spikes. Statistical measures support that interpretation and indicate that the gauge model performs best. How can we use those results? Further research can be done for different markets, different time frames, different models such as the E-gauge and the gauge and mean model, and with more practical implementations such as in the portfolio management of volatility trading strategies, for example, or using volatility targeting portfolio management tools. Here you can see my references, and additionally in the description you can see a link to a OneDrive folder where I've saved all the codes I've done in Python and this presentation, my paper and all the images, so you can evaluate my work and maybe replicate it. And thank you for your attention, and I wish you all the best for the exam. Thanks.